Hey, what I'm going to do right now is talk about integer exponents. Not only integer exponents, but what we're going to do with integer exponents. A lot of times, what happens with math is that somebody messes around with the numbers enough that we realize that there are patterns in the process. And if there are patterns that we can identify and actually use those to take shortcuts, we should. Because especially if we can prove somehow that they work every single time, all right? And that's really what identifying patterns in mathematics is all about, is if I can take a shortcut, I should. Why make more work for yourself? The problem is it needs to be something that happens every single time and not coincidence. So what I'm going to talk about now is what to do with integer exponents. Now, the goal that we're looking at here is to know and apply the properties of integer exponents to generate equivalent numerical expressions. So really what we're looking at, this in a little simpler terms, we're going to know what we're doing with the exponents, and we're going to apply the rules, not just integer exponents, but what are the rules or what are the patterns that we can use to solve problems in a simpler manner and make things easier for ourselves. And then we're using integer exponents. So integer exponents, we're talking about the whole numbers, like 1, 2, 3, 4, 5, so the counting numbers, the whole numbers, and we're talking about the zero, and we're also talking about negative integers, so the opposites of the whole numbers. So -1, -2, -3, and that's going to be a real sticky point. So I'm going to make two videos. I'm going to make one that is about the rules, and then I'm going to make a separate one that talks just about the negative integers as exponents, because a lot of people get confused on that because it's just crazy. Like it has to be a negative number, and it doesn't. All it really is a notation or a way that we write it down to remind ourselves of something else. It's like when we put 3 on the outside of x plus 2 in parentheses, the 3 needs to be distributed. It's distributed, distributed. That was distributed. That was weird. Distributed. So as the 3 gets distributed and we draw our little arrows, we are reminding ourselves of what's going on. That's why we wrote it that way, is so that there were 3 of the things inside the parentheses, and then we have to use that. The same thing with the negative exponent. It just turns out that that's just a notation. And the easiest way that I remember it is just to change it. Just like if I say 3x plus 2 in parentheses, I did 3 times x and 3 times the 2, which is a 6. So it's 3x plus 6. I change it. I simplify it into something else. The negative exponent just tells me, hey, you can't do this. Change it so you can. All right? That's all it really is. And but it's a very confusing thing, and I'll make a separate video for that. So looking at here, equivalent numerical expressions, we're really talking about simplifying the thing. So for instance, you wouldn't walk around saying, I have $5 squared in my pocket. You would say, I have $25, unless you're one of the cool kids. Okay? But you also wouldn't say, I have 5 squared plus $5 squared in my pocket. You would say 50, right? Maybe? Let's check it out, all right? So here, what I have is my goal, and then what we're looking at, it, like I said before, we have my mathematical practices, a pattern. It's a pattern. So I'm looking for patterns that might help me with my math. So here, what kind of exponent problems or what kind of power exponent problems are we actually going to see? Well, what if I had, if you have something like 2 plus 2 plus 2, we recognize this as repeated addition, and repeated addition is really multiplication. So I have 2 plus 2 plus 2. I don't have to keep adding. It's the same number each time, and it's repeated 3 times. So I'm going to 3 times 2, which is really 6, because this is a group of 2 3 times. A group of 2 3 times, which is 6. So repeated addition becomes multiplication. But what happens if we have repeated multiplication? What if we have 3 times 3 times 3 times 3? What are we going to do with this number? Well, let's put another one on there just to be cool, right? So if this was 3 times 3, I would just call this 3 squared. And since this one is 3 times 3 times 3, well, there's 1, 2, 3, 4, 5 of them. So now I have this. So repeated addition becomes our powers, where we have our base and our exponent. So repeated multiplication, I hope I said that right the first time, repeated multiplication becomes powers. We have our exponent on top of our base, and here's a base with a different exponent. So what happens if we had a situation where we had a power times another like this, right? What if we had a number that had an exponent on it times another number that had an exponent on it? And if I wanted to expand this, and if I wanted to expand it, I would say, you know what, I know what this looks like. It looks like that. So it was 3 times 3 times 3 times 3 times 3, 5 of them, times, that looks like that, 3 times 3. So what happens here, there's 1, 2, 3, 4, 5, 6, 7. If I was going to think about my repeated multiplication, becomes a power. So I've got 7 of these things. It actually turns out that this is 3 to the 7th power. Because if I follow this, and there's 2 of them, put a 2 there, 5 of them, I put a 5 there. Now if there's 5 times a 3 with another 2, and it's all the same multiplication, I can do that. So where does that 7 come from? Well, it comes from the idea that we have the same base. We have the same base on each of these. And if we're going to use that base here, what happens with the 5 and the 2? Well, we just had 5 of them, and then we had 2 more. 2 more than 5 is 5 plus 2. And this whole thing is going to equal 3 to the 7th power. So it looks like if I have the same base, I can just add the powers or add the exponents, and that's my new thing. Well, it turns out that that is what happens. If I have 4 to the 3rd times 4 to the 2nd, and I have the same bases down here, this is really going to be 4, and there's 3 of them here and 2 of them here, which is 4 to the 5th. And that would be 4 times 4 times 4 times 4 times 4. If I had a 2 here and a 3 as an exponent, that's 3 2's multiplied by each other. And then if I multiply that by another 2, that was, let's say the first power, 3 plus 1 is 2 to the 4th. Then, what if I had something like this? 2 to the 3rd power times 3 to the 2nd. Man, this is going to be really cool. Wait a minute. I don't have the same bases. So if I expand this one, I have 2 times 2 times 2 times 3 times 3. I can't combine this into one idea, and I can't make it 6, because then it would be a 6 times, to the 5th, and that's going to be really, really a large, it's going to be a great number. This will not work, and the reason it won't work is because we don't have the same bases. So we don't have the same bases, we can't put it together, we have to leave it like this. This is simplified until we realize that 2 to the 3rd power is 2 times 2 is 4 times 8 times 4. 2 times 2 is 4 times 2 is 8. So the first part is 8, and then the second part, 3 times 3, which is 9. This number is 72. So 72. All right? So this becomes a 72 here. And if you look at this, 2 times 2 times 2 times 3 times 3 is 72. And if we had mixed this together and made it a 6 and put it to the 5th power, 6 times 6 is 36. And then you multiply that by 6, you're over 180, right like that in the second one, or the third exponent. And it's just not going to work. So this is how the powers work when you've got 1. Ooh, that purple is really tough to take off the board. So we have a rule now. It looks like we have a rule that if we have 2 powers and we have the same base on each of those powers, we can just add them. So if I have my rule here is going to be, if I have a number and I have an exponent on it, and I'm going to multiply this number by the same number with a different exponent on it, I have a, and then it's m plus n in the top. Now this looks very complicated, but really what it is saying is if I have 2 and a 3 up here, and I have a 2 and a 2 up here, it's going to be 2, 2, 2, 2, and then 3 plus 2 is 5. Okay? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Okay? So 2 to the 5th power is 32. And that's how that works. So here's my first rule. That if I have things that are multiplied by each other and they're the same base, all I have to do is add my exponents. And that was easy. So how about my next idea? What if I was going to divide something that had the same base on it? So what if I had this? If I had 4, let's say we're going to take 4 to the 5th and we're going to divide it by 4 squared. That's exciting. So if I expand the top, this is 4 5 times. 4 times 4 times 4 times 4 times 4. And this is 4 times 4, twice, 4 times 4. Now, what are we going to do with this? Well, I could multiply everything out, and I could realize there's a 16 on the bottom and there's a greater number on the top. Or I could realize I was multiplying things by 4 on the top, and then I'm dividing by 4 on the bottom. So what if 4 over 4 could be simplified and 4 over 4 could be simplified? All I would have is what's left over there. So why don't I do that? 4 over 4 is 1, and 4 over 4 is 1. So these are actually going to leave the problem, because 4 times 4 times 4 times 1 times 1, these are not part of my solution. And then I end up with 4 to the 3rd. 1, 2, 3 is all that's left. All right? So it would be 4 times 4, which is 16, times 4, which is 64. All right? So what happened? How did I get a 3 over here? Well, do you think it's a coincidence that there was a 5 up here and life continues. It's the Army. I'm going to wait for them. They're going to have to call me back later. So it's 1 and 1, 4 to the 4 cubed. What happens if we have 5 and a 2? Do you think it's a coincidence that 5 minus 2 is 3? I don't think so, because we had 5 on the top, and we took these 2, and they made 1s out of 2 on the bottom. So we had 5, and then we subtracted 2 because they were kind of canceled, made a 1 here, which left a 3. So maybe our new rule for this is, if you have something with a power on the top and something with a power on the bottom, you can actually 5 minus 2, and that's going to be your answer for the exponents. And that's what happens. That is what happens. So our new rule here is, for this type, is if we have multiplication, we just add the exponents. But if we were to have a to the m over a to the n, whatever number is up there is going to subtract this. So this is going to be a to the m minus n power. Pretty sweet. So there's our second rule. So here's our first rule, and here's our second. Now, does this work for things that don't have the same base on them? Well, let's check it out. We've got 3 squared, and we've got 2 to the, oh, let's make it 3 cubed, excuse me, and 2 squared. I'm thinking ahead. Let's expand the top. 3 times 3 times 3. Pretty sweet. On the bottom, 2 times 2. And let's take care of our ones because we know there have got to be ones in there because we're dividing by something. So let's get rid of our ones. You know what? This number is going to be 3 times 3 times 3, which is 27. And this number is 2 times 2, which is 4. There's nothing in common factors between a 27 and a 4 because the only things that are factors of 4 are 1, 2, and 4. 27's only factors are 1, 3, 9, and 27. There's nothing in common. There's nothing in common. There's nothing in common. Nothing makes a 1. It all has to stay. This is as simplified as this gets, unless you want to be a pain in the neck and make it into a mixed number, you know, or a decimal. But it hates me some decimals, so I'd rather not, okay? So here's our second rule. If we're multiplying, add them. If we're dividing, subtract them. Pretty easy. Now, I'm running out of room here, so there must not be too much else to go over. Here's something else. What if we took 5 squared and we did this to it? And we cubed it. What would we do with 5 squared cubed? Now, if that thing in the middle there was an x and we just wanted to cube it, we would say that this was x times x times x. X is going to be cubed. X times x times x, because there's 3 of them. So if we're going to do the same idea here, what this really means is there are 3 of these multiplied by each other, which is 5 squared times 5 squared times 5 squared. And if we go back, this idea right here is this idea here. So we're simplifying this to this, and if we have the same base, the numbers on the top just get added. So it's 2 plus 2 plus 2, which is going to be 6. So this is really 5 to the 6th. Well, is it a coincidence that 2 times 3 is 6? The answer is no. So the simplified part of this is whatever's in there has to be subjected to that. And if it's going to be repeated that many times, it's just back to the repeated addition. The repeated addition of the exponents, and repeated addition is multiplication. So all we have to do is 2 times 3 and we're done. So how does that work? Well, another example of it. This is, if I had 2 cubed and I took it cubed, all right, this is going to be 2 to the 9th. 3 times 3 is 9. If it was 2 squared times squared, this is 2 to the 4th, because 2 times 2 is 4. Okay, so we refer to this as a power taken to another power. So if you have something that is a power and it's taken to another power, here's my third rule. If I have a to the m and I take it to the nth power, so a to the nth power taken to the nth power, this turns out to be a m times n power. You can barely see that. There we go. Okay, so breakdown of this, make it real simple. If I have the same base, and it's always got to be the same base. If it's not the same base, you got to get rid of it, right? If you had some, and think about it, like if you're mixing some songs, and you were like, you're DJ, and you're gonna mash this thing together, and you're gonna make it flow. You don't want to train wreck, is what they call it. You've got one bass going, you've got kind of a beat going, and then you come on, and you got to have another beat. Mix it. You gotta join it, and then go on. You can't just let's get in there, right? You've got to have the same kind of idea going. You've got to have the same kind of flow going. If you don't have the same flow going, this doesn't work. If you don't have the same beat going, you can't put it together, okay? Same beat, got it. Same beat, got it. But if it's different, it will not work, and you have to just expand it, okay? So we've got the same base, and we're multiplying. We add the exponents. If we have the same base, and we're dividing, we subtract. And if we have a base, taken an exponent to another exponent, or a power to a power, we multiply. This is the whole problem. This is the first part of all of these rules for exponents that we're going to talk about. Okay? Now, the other video that I'm going to make deals with what if, and I'm going to explain why, what if we had a 0 up here for an exponent, and why that exponent, why that always has the same answer to it. No matter what base there is, if you put a 0 up here, we always get the same answer. The other thing I'm going to talk about in the other video is negative exponents. But this right here deals with everything that we're going to deal right now as far as the rules are concerned. The other two things are like the 0 power, the power of 0, is something that comes up, and you just need to know that's what this is. All right? You need to know what the answer is every time for the rest of your life. That's what it is. It never changes. And the other piece of it is, what are we going to do if we have a negative exponent? Well, we're going to rewrite the problem so we can actually work with it. Okay? So join me for the other video.